It was started by the Taoists in ancient China. They were the first scientists in the fact that they invented experimental pharmacology with the goal of living forever, extending lifespan. So in essence, gerontology is the oldest science, and it's collected many myths since its the beginning, some of which are listed for you there. I'm not going to spend very much time on old mythology. You can see them there. There are many immortality myths. Dracula was a very successful practicing gerontologist. Frankenstein monster doesn't age. Ahasuerus was the wandering Jew who was sentenced by Jesus since he mocked him to stay till the second coming. So there are many myths like that. And then there are antediluvian myths, that is the extended lifespan of the pre-flood patriarchs, and Hyperborean myths beyond the west wind like Shangri-La and other places. So I think you know many of them, and they've pervaded our culture. I'll go a little bit, though, to will take us up to a modern myth, which has to do with aging in kind of a negative sense. So this is you've all seen Star Trek. And in Star Trek, that's a modern science fantasy myth. We see great starships going from one galaxy to another, traveling at the speed of warp drive. And we see human beings assembled and disassembled, teleported over great distances. All of this is taking place in the 23rd century, 300 years from now, in Star Trek. And we see the medical situation at that time where the doctor points a little gadget about the size of a men's razor at somebody's neck, and zingo, they're cured of cancer or healed of whatever ails them. So all of those great things are going on. But if you look at Star Trek, you'll find that there's an inconsistency in the minds of the writers, because Kirk will often say, or sometimes say, he'll say, when I was a cadet in the Space Academy 30 years ago. So what is going on? The writers of Star Trek, they're envisioning and taking for granted all of these fantastic advances, but it never occurs to them that 300 years from now, the biology of aging will also have advanced. So this is kind of what goes on in the public mind. This is one of the things that I call this the Star Trek inconsistency. And when I tell this to people who've seen Star Trek all the time, they look at it and they say, yeah, I never thought of that. And so everybody doesn't think of that, and we've been culturally conditioned not to think in terms of the possibility of extending lifespan. That's one of the problems that the anti-aging movement has, is with its kind of cultural conditioning. So let me go on to some other cultural conditioning things. The next one is something I call the Struldbrug obsession. If you remember Gulliver's Travels by Jonathan Swift, Gulliver went around and he came to a land where there was a subpopulation of people who got older and older and never died, but they got more and more senile and more frail. And they were called the Struldbrug. So this is the Struldbrug obsession that many people, when they think about anti-aging stuff, they get the idea that we're going to create a society of very doddering, frail people. Now, Betty Friedan's current best-selling book, I should stop here to mention that this is also seen in the myth of Tithonius, and in modern times, the best example of the Struldbrug obsession is the movie Zardoz. So I'm going to show you a little bit from Zardoz, a film that came out about 10 years ago starring Sean Connery, and this is a scene from that. Anyway, Betty Friedan's current best-selling book, The Fountain of Age, is a very good account of the Struldbrug obsession in these terms. About 10 years ago, Betty attended a session of the Gerontological Society of America, a session that was devoted to the implications for society of increasing the lifespan. I was one of the speakers of that, and Betty comments in her book, quote, But the very idea of extending the lifespan seemed, she's commenting in her book following the reaction to my talk at that meeting, quote, but the very idea of extending the lifespan seemed strangely threatening to the other distinguished gerontologists in the hall. And she describes another speaker as warning, quote, that such research was leading humanity towards a gerontological winter, conjuring up the specter, this is all from Zardoz, of miserable old people losing their vision, hearing and reflexes, their heart and lung capacity, and mental powers. People who never died, just got older and older, and more disabled, end quote from Betty Friedan. So that's the Struldbrug obsession, as seen also in Zardoz's movie, and of course it's absolute baloney, but it's very prevalent in society. So we have to deal with those two things tonight, the Star Trek inconsistency and the Struldbrug obsession. So I want now to go a little further and disabuse you. I don't think I need to in this group of the Star Trek inconsistency and the Struldbrug obsession, and present some scientific evidence. They're both quite wrong. I'll then briefly discuss why people are so hung up on these two things, this inconsistency and this obsession, and then discuss a little bit about what I think society may be like in the 21st century. Okay, now, first the scientific evidence. There are two types of experiments that show that this is quite inconsistent, these things. Now, the first one was published a little while ago in Science by Sohal from his laboratory, in which he showed that by putting extra copies of genes of superoxide dismutase and catalase in Drosophila, that he could substantially influence the survival curve. I think extending the survival curve is the ultimate test of an anti-aging program or procedure. And you see here in the slide, you see two survival curves. The one on the left is the one of the normal Drosophila, and that on the right is that of Drosophila with extra copies of these genes. So this is really the first example that I think is outstanding or convincing of extension of maximum lifespan with a squared survival curve, except for caloric restriction. So it's now been done by two techniques. This is a more definitive one with the molecular genetic manipulation, since we can track down what is actually going on. This technique needs to be applied further to mice and other animals, the Sohal technique. I think that's in progress in different laboratories, but in any case, the door is open, and species-specific maximum lifespan has certainly been modified now by two techniques. Perhaps more pertinent interest to human application is the work done with higher animals and the demonstration that caloric restriction will retard aging and extend maximum lifespan. So I'm going to spend a little bit of time on that, although I'm not trying to sell you on the idea of caloric restriction. You can read my books if you want that. So this is not really a pitch for that, but to use that to make other points. Now here you can see some survival curves. If you look at the upper part of that slide, and the survival curve on most to the left is unrestricted mice. This is work done in my laboratory. And then the other survival curves that you see there are increasing restrictions. So 10% extends lifespan more than no restriction. And the more the restriction is instituted, the longer the lifespan, the better the survival curve, out to the point where you get into actual caloric starvation, and then the animals die. But up to about 50% restriction, there's a progressive retardation of the aging program and extension of lifespan. It's also true in caloric restriction that the time of reproductive senescence is delayed, and the age-specific incidence of essentially all the diseases of aging are moved to the right. And these are two very good indications that aging is actually being retarded. So now let's consider a little bit the Struldbrug obsession and then come back to caloric restriction. What you're getting in caloric restriction is the kind of curve on the right. I've projected this in human survival, but what you see is if the curve is moved to the right, that the diseases of aging, which are represented here by the little hills under the curves, they're also moved to the right. And the period of frailty, which I've arbitrarily said here is the period beyond the 50% survival point, that's kept the same. It's just the same shaded portion of the curve, but if the curve is shoved out to the right, it becomes a smaller part of the total area under the curve. So that by retarding aging, one is actually decreasing the number of feeble people in the overall population, exactly the opposite of the Strollbrug obsession. A couple of slides just to illustrate those points. Here you see calorically restricted animals, and their diseases are shown in the two curves on the right, and they're occurring at a later time in life than in the curves on the left, so that age-specific diseases occur earlier. Some of the things I'm going to show you in humans when we get to the biosphere experiment, I'll just show you briefly in animals. On the left here, this is blood cholesterol in calorically restricted rats. The upper curve is normal rats, the lower cholesterol you see in the lower portion of that curve. If you look at blood sugar, there's a marked decrease in calorically restricted animals in fasting blood sugar, a decrease in glycated hemoglobin, very good signs that the glucose metabolism is in a much better state than normal. Now, a couple of functional tests deserve illustration in terms of counteracting, say, the Strollbrug obsession. What we see here is on the left, a test of mental function, on the right, a test of complex skeletal-muscular coordination. On the left is the ability to run a maze, and the red bars are control animals that are not restricted, and that shows the number of false turns they make, and you see with age. So when the mice are young and they're restricted, there's not much difference between the restricted mice, the green, and the control ones on the right. But as they get older, you can see that the control ones, the non-restricted ones, make a lot of false turns in running a maze compared with the green bar. On the right is the ability to navigate on a rotating rod. If you hold a rotating rod, like rolling a log about 6 feet off the ground, put a mouse on it, they like not to fall off, so they kind of run on the rod, and it's like log rolling, and it's a complex musculoskeletal test. So that's the number of times they fall off the rotating rod. If you see on the two bars on the left, when they're young, it doesn't make too much difference if they're calorie restricted. But throughout life, you see that by the time they get to be old, that the old restricted mouse, in this case, is still staying on the rotating rod as well as a young mouse, whereas the older, normally fed mouse is falling off quite substantially. Now, another way is just to see what animals look like if they're restricted. And I hope you can see them fairly well. The mice, all of these mice are about 39 to 40 months of age, which is equivalent to 90 or 100-year-old human. Those on the left are restricted, those on the right are not. And they have gray hair, they don't take care of themselves. And they obviously look older. They look ratty, I say sometimes. Okay, now I want to show you that many of these things do apply to human application. This occurred during a time that I was in Biosphere 2, which was from 1991 to 1993 for 2 years. Biosphere 2 is a closed ecological space near Tucson, Arizona, about 3 acres in size, where 8 people were sealed in for 2 years, and we had to run everything. It's completely sealed, and the exchange with the outside atmosphere, for example, is less than 10% a year leakage as compared to a skyscraper. If you shut it up entirely, you still get about 25% exchange with the atmosphere per day. So it's kind of the tightest large structure that's ever been built. And the bottom is a stainless steel plate, so that it literally floats upon the earth. There are a number of biomes inside Biosphere 2. What I just showed you, we'll go back to it. You see right to the left of that dome is one of the structures. That's the biome, the glass dome over the desert. And so we look inside. This is the desert biome. The desert came from Baja California, Israel, South Africa, and Australia, plants from around the world to make a complicated biome situation. This is the rainforest biome from outside, 85-foot tall sealed structure. And if you look inside, that's the inside of the rainforest biome. The purpose of the biosphere was to serve as a prototype space colony, totally self-contained unit, which would be somewhat like mankind will use when he gets onto other planets. And it's also a closed space for a number of ecological investigations that I won't go into. There's also an ocean in the biosphere, which is the only ocean in Arizona and the highest ocean in the world. It's mainly from Caribbean undersea life. It has a living coral reef and fish and so forth. There is also a savanna with grasses from different biomes from around the world, and an agricultural station about half an acre in size where we had to raise all of our own food. And in animal quarters, we had goats, chickens, and pigs. I'm just outlining for you the structure of the mini world in which the calorie restriction experiments took place that I'll be telling you about. This is the human habitat. The upper portion were the apartments where we lived. The kind of phallic tower sticking up there is the library. And then behind that is the agricultural station. And the habitat itself contains, besides apartments, as a medical facility, which I put together, and shops, machine shops and things of that nature, an analytical chemistry shop. So in September of 1991, there are 8 people sealed in. I was one of them. I was the medical physician, medical officer. I think one of the most difficult things about the biosphere for me was after being in research and pathology for 30 years and mainly doing research and not dealing with patients, I had to suddenly pass the Arizona State Board, which is one of the more traumatic parts of being a biospherian. Anyway, as I said, the biosphere is like a Garden of Eden on top of an aircraft carrier, in the sense that you have all the plants that I showed you above, but underneath, on the stainless steel plate, there's a big, tremendous basement, because everything has to be run. The air has to be circulated. All waste and water is recirculated. Energy can come in. If you're as small as an electron, you can come in, electricity or light energy from the sun, but anything as big as a molecule is supposed to stay out as much as possible. So everything is self-contained. You couldn't call the plumber or the electrician. We had to run everything inside, and there was a huge amount of technosphere to take care of which I just showed you. That besides being the medical officer, I had to repair a lot of the computer systems, which is what I'm doing here. Everybody had to do multiple jobs. We're here working in the carbon dioxide scrubber, kind of infamous infernal machine to take care of excess carbon dioxide. Okay, now after the closure of the biosphere too, due to lower light than expected in Arizona and more problems with pests, we couldn't raise as much food as we had projected that we could raise. So we were on about an 1,800 calorie diet, but we were committed to not bringing in food, since the integrity and the purpose of the experiment was to be totally self-contained. So inadvertently, this became the first human experiment in caloric limitation. It wasn't really planned. And I think what was almost a miracle was that somebody with my background should be the medical officer inside. So I haven't quite figured out why that happened. But anyway, so we were on a very nutritious diet. So it was a super nutrient-dense diet. I'd been in on the planning of what we'd be raising, but it was very low in calories. And we had a great workload to do. It was like a little bit like the Cultural Revolution in China, that all the intellectuals were suddenly out in the fields. I've spent plenty of time working in a rice paddy. I could go to China and do pretty well or Japan pretty well in a rice paddy, which is what you see going on here. Raising and threshing wheat. Threshing wheat, I'm threshing wheat here. I know how to do all of those things. Butchering the animals. We had goats, chickens, and pigs in the biosphere. And everybody had to cook too. Every 8th day you had to spend 10 hours cooking for everybody else. So it was a 65-hour week. It was a very labor-intensive deal. That's why I injured my back quite a bit with all this labor inside. The next oldest person was 42, and I was about 67 when I went in. So I had to struggle a lot to keep up with everybody. Everybody had to do the same amount of work. I had quite a good medical facility inside, clinical laboratory, portable x-ray machine, electrocardiogram, small operating room, and so forth, and a good bacteriological laboratory. Okay, so we were on a calorically restricted regime, and everybody lost a great deal of weight. The men lost 18% of body weight, the women 10%, and the men got down to about 7 or 8% body fat, and the women to about 12%. And that's very low. 5% body fat in men is the point at which you start resorbing bone, and 10% per women. So it was a severe caloric restriction. You can see the weight curves here, if you can see them, for the males, and weight curves for the females here. But the extent of the restriction probably is indicated better in the next slide of me. So I looked like I just got out of a concentration camp, I think you might say. I looked kind of mad. Maybe I heard that I hadn't gotten a grant or something. I'm not sure. Anyway, I'll come back to that. This is one of the ladies. They lost a great deal of body weight also. None of the women had any menstrual irregularities, though, and this is very unlike this kind of weight loss in women. Women who get down to this lean fat mass generally are amenorrheic. None of the biospherian women ever missed a period. So it's an odd kind of nutrition. It's not like usual starvation, in which case people are lethargic, develop peripheral edema, and fatigue and so forth. We didn't have those problems. We just looked bad in these photographs. This is a group portrait of 6 of the biospherians, and so you can see that they were all pretty thin. One didn't want to be in the portrait, and one had to take the picture, but these are 6 of us. Okay. However, I want to emphasize again that this is an unusual kind of nutrition because we were doing a tremendous amount of physical labor and mental labor. It was a 65-hour week, so it's quite unlike starvation regime or what like other people like the famous Minnesota study when people lost about this much weight over about 6 months on a, however, not very nutritious diet, and they were sick, and we were very healthy. I'm doing a great deal of labor here, as you can see, and I think the main trouble I was having in that picture was that I was about to lose my pants. That was a problem when you lose that much weight and you can't go out to a tailor. Right? The young lady that you saw who looked so thin is here again pictured, and she was doing an enormous amount of work despite her seeming emaciation. She not only did hand field agriculture, which I was also doing, but she was the marine biologist inside and was spending about an hour and a half almost every day underwater taking care of the ocean. Scuba diving is a very intense physical activity. So it's an odd kind of nutrition, not like just starving. A number of the things that I was able to observe in the medical system was there was a great fall in blood cholesterol, as we also see in animals in calorie restriction. I don't know whether you can see the slide very well, but the cholesterol went down from a pre-entry level of an average of about 198 for the 8 biospherians down to an average of about 120 to 125. This is a pre-teenage level of cholesterol in our society. And that was true for both the men and the women. This is the level for females. The heavy line is the average level. There was also a great fall in fasting blood sugar, as shown here. It went down from pre-entry level of about 95 or 98 for everybody to an average level of about 70 to 72. There was also a fall in glycated hemoglobin. And this is the fasting blood sugar for the women, which also went down substantially. And there was a great fall in blood pressure. This shows in the upper portion systolic pressure for the men and diastolic pressure for the men also. So everybody's blood pressure went down to something like 95 over 60 or less for all the biospherians inside. This is the average blood pressure of the female, systolic above and diastolic down below. Now these are the summation of some of the things that I've observed. There are many things that I couldn't do inside the biosphere in terms of following the course of this serendipitous experiment, because my laboratory inside was not as big as or as competent as a university laboratory, but I was able to freeze blood and serum and plasma from all the biospherians at periodic intervals at minus 80 degrees inside and retain it and brought it out with me. So I'm continuing in retrospect with all of the work so that I'm now able to do more complicated things that I couldn't do inside. This summarizes some of the overall work. The fasting blood sugar on the left column, you see rodents on the right, calorie-restricted rodents, on the right humans. So I'm comparing whether they're showing the same responses. Fasting blood sugar is down very much in both. Insulin is down in both. Insulin in all biospheres is less than 5. Normal is 5 to 25. Cholesterol was markedly down in both animals and humans. Triglycerides, white blood cell count, calcitonin is down in both, glycated hemoglobin. And then when you get to growth hormone T4, T3, and PTH, there's some discrepancies, but these are not really decided in animals how they are. So the hormonal situation is not clear at the moment. Glycated hemoglobin is down. So on the whole, everything that I'm finding so far shows a very good concordance with what we see in animals on a caloric restriction. Now, if we look at all of the things that animals show, on the whole, as seen here, one calorically restricted animal show a great prolongation of survival. Well, you can't show that in humans as yet because it would be a 50 or 60-year experiment. Animals also show in caloric restriction that the diseases of aging are greatly decreased in frequency and they occur at a later age. Again, it's difficult to show this in humans because it's a very long-term experiment. However, the third thing that animals show is that there's a wide variety of biochemical, immunologic, and physiologic changes in animals on caloric restriction. And these, so far as I'm able to show, seem to be also seen in humans on this kind of diet. So the way to think of that, when I get done with this, I hope to be able to say, I don't think so much in terms of biomarkers in this. Another way to think of this kind of a study is if the DNA repair is increased in caloric restriction, and that corresponds to the DNA repair theory of aging. Caloric restriction induces changes in free radical production and free radical scavenger production, which is what you would expect to occur if it prolongs lifespan in accordance with the free radical theory of aging. Changes in the immune system are also brought about by caloric restriction, which would correspond to the immunologic theory of aging. Well, I'm showing many of these in humans so that if humans show the same thing in all of these things that correspond to the various theories of aging, if humans show all the same thing and they don't live longer, then none of the current theories of aging are correct. And I think that's not true. So I think that's even better evidence than trying to show biomarker changes. So that's kind of the goal that I'm working towards in these experiments. I just thought I'd show a slide since we're going kind of the extremes of how long we think we can extend lifespan. I'm generally regarded in the gerontological fraternity as fairly radical kind of guy. On the other hand, the nanotechnologists who are showing very promising work. There's a good article by Marvin Minsky in a recent Scientific American, and they're talking about really extending lifespan unto immortality, and they're very reputable people. Mirsky is the winner of the Japan Prize in Mathematics, which is kind of the Nobel Prize in Mathematics, and is one of the top guys in the artificial intelligence division of Massachusetts Institute of Technology. So he would be regarded as far out more radical than I am, let's say. And then very conservative position is that of Len Hayflick, who thinks that life extension is not possible and not desirable. So I tell everybody that I'm just a moderate in that area. See? Now let's come back to the Star Trek inconsistency and the Struldbrug obsession. I think the experiments with the molecular genetic manipulation in flies and the calorie restriction experiments shows that these are not true, but why are people so hung up on that? They're hung up because of two things, because of one, apologism, and two, because there are a lot of false myths and failed searches in the history of gerontology. Examples of apologism. Man has had to deal throughout his conscious history with the knowledge that he dies eventually, and he doesn't like to do that. So he's invented a lot of ways of not thinking about it, or thinking about it more cheerfully. And this comes to apologism. The best example of that is religion, in the sense that any religion that promises a life after death gets rid of the problem of thinking about dying. So religion is kind of apologism in that sense. But the apologists have said that extended lifespan is against the natural or divine order, or it's unnecessary, the religious reason, because death is not really the end, or everyone will end up disastrously old and decrepit, the Struldbrug inconsistency. Living too long will be boring, that it'll interfere with evolution, that society will stagnate. These are all the examples of apologism that you'll find throughout the centuries in literature. Apologism seeks to provide acceptable reasons for the inevitability of age and death. And if you look at the great thinkers and writers in human history, you can divide them into the people who are apologists, which are listed here as Lucretius, Cicero, Marcus Aurelius, Aristotle, and the list is much longer. And then those on the other side have been Roger Bacon, Francis Bacon, Descartes, Paracelsus, Ben Franklin, and so forth. So there's been a big division of thinking for many years, and the inbuilt inability to think beyond the Star Trek inconsistency is a fallout from the centuries of apologism. But there also, in the history of gerontology, have been a lot of myths and failed searches in longevity. Ponce de Leon, Brown-Séquard, Metchnikoff, Bogomolets, they all promised to extend lifespan, but it didn't work out. So those failed searches have given kind of a bad name to the subject, which I think we're in position to overcome, certainly during the next so many years or the next century or whatever. In terms of the effect on society, it's amazing that there's been very little, there's been a lot of off the top of the head thinking about the effects of a long-living society, about what it would have on social institutions and so forth. But there's been almost no professional thinking about this. And the only real professional thinking that I know is that of Larry Kotlikoff, professor of economics at Yale University, who has very carefully, with advanced economic mathematical thinking, gone over and compared the benefits of a curve squaring methodology with a span extending methodology. And he finds if we only, it's shown up here, but I'll read it to you, it's probably not visible, with a curve squaring technology on the left, you get a decrease in gross national product, decrease in housing starts, increased unemployment, increased unemployment insurance benefits. This is the results of a more squared survival curve without doing anything about the aging process. On the other hand, with extending lifespan in the way that we're talking about, his economic calculations come up to a 12% increase in capital intensity, an increase in ratio of productive to non-productive persons, and an increase in average consumption per year. So it's a very positive projection, and that assumes that we're doing it with a curve like the ones that I showed you earlier, when the area under the last portion of the curve of feebleness is no greater than in this present society, but the period of the youth and of the young old is extended, but the period of the old is kept the same. And this is actually what we do find in mouse populations that have had their lifespan extended. Now, another way of thinking of the future when lifespan is extended is shown here. This is from a recent article in the Gerontologist magazine by Matilda and John Riley. They've divided on the left side, you see here, that aging today, or the lifespan today, is divided into young, middle, and old ages. And the young period is a period of education. These are the blocks that are building up there. And the middle period is one of work, and the last period is one of leisure. So it's kind of stratified like that, and they call this an age-differentiated society. But an age-integrated society, which is what I think we're heading for with extension of lifespan, these blocks are turned up on end. And you see them there where you get educated throughout life. The education continues, work continues throughout life, and leisure continues throughout life. So that's a whole restructuring of the way we're doing things. So I think that is the future way that society is heading. It's interesting to realize as we approach the end of the century that many of our children or grandchildren, depending on where we're starting at, will be living in 3 centuries. And as they're born before the year 2000, they'll live through that century and live on into the 22nd century. So this is a new prospect for everybody. I think it's important to realize that one of the main things in the future that we have to do beyond extending lifespan is to take care of our own biosphere, just as we had to take care of our mini-world, Biosphere 2, and we need to take care of Biosphere 1. And I think one of the things that we'll see with a long-living society, the long-living cohort will make a very substantial contribution to taking care of Biosphere 1. Thank you.
Thank you, Dr. Walford, for an interesting peek at what the future plans to hold for all of us. We all here feel you're right.